Mm. Mm. Okay. Okay.
It's been a while since I could hold my head up high, and it's been a while since I first saw you.
Practice tests.
And it's been a while since I could stand
Yeah, this is a great equation sheet.
my own 2 feet again. And it's been a while since I could call you.
You have all of the fundamental constants, magnetic field forces. Dude, this should be easy. Here, let's look at the Oh, our test. That's what it stands for. Alright. I'm procrastinating, bro. I just gotta start. 3 charged balls are arranged at the vertices of an equilateral triangle, as shown in the figure, with A equals 2 meters. The balls have electric charge Q1 equals Q2 equals Q3 equals negative Q1. Okay. So these are both negative charges. Q1 is positive. They're all of equal magnitude. The 2 are opposite direction. Below, answer the first with algebraic expressions and calculate the numeric values. If the result is a vector, write it in column notation. What is the electric field at the location of Q3? So obviously, if you look at the equation, electric field is dependent on distance from the point charge. So this should be sum of a bunch of point charges. Where is it? Oh, electric field, electric field, electric field. Electric field of a point charge is equal to this, right? This thing right here. Bro, what is happening? This sucks. Electric field is equal to this. Let me insert the equation sheet. One second. Exam 1 equation sheet. We get together one another. Insert. Okay, this is much better. get rid of this. But it's this, which obviously you have R. So if your R is 0, you're obviously the electric field is 0. So it's just below answer first with algebraic expression and calculate the numerical value. Okay. Oh, it gives you Y. And then obviously this is 1/2 A from here to here. So the force on, okay. Let me think. Oh my god, please. What the fuck? What is the electric field at the location? The contributions of Q3 are none. Right? So what's R squared? You know this. You know this. You should know this. You should know this. This should be quite easy. This is really fucking annoying. Okay. So it's... these constants get filtered out. So you literally just add them. So it's Q2 it's that. So it's essentially so you just write it in terms of Q1. So it's negative Q1 divided by, so R squared in this case, I can write this in vector notation. I mean, it could be 1 over that. Well, this is a magnitude. This is a magnitude. I don't know what I'm doing. It's negative Q1 over R2, 3. So from 2 to 3, okay, it's just A squared. And then you have to multiply it by your unit vector, which is literally 1/2 A I hat, well, plus A over 2 J hat over A. Let me just erase all this. They want it in vector notation like this. It's A over 2 times 1 over a. And then it would be square root 3a over 2. Wow, this is really, really annoying. This is negative. That's it. That's what it is. That's my calculator. Should just be in the I hat. It shouldn't be as hard as I'm making it. I know that from Q2 you have this, from Q1 you have this, you end up with this. So I mean, you could just write it out in the J hat, but yeah, I'll write it out as much as I can. It's just too much, bro. One over 2a squared I hat plus all these a's should cancel. 3 square root 3 over 2. This is negative. Left with J hat. Sorry, left with I hat. I'm retarded. It's just K. Isn't that just K? .99 times 10 to the 9th. Multiplied by, these just cancel. You get rid of the 2 on the bottom. Wait, what? Yeah, just get rid of this. So it's all in standard units, all in SI unit. A squared 4. Oh, that's ridiculous. If I knew it did that, I would have understood. Why do they care about column notation so much? It's newtons per column. 674. What is the electric force acting on charge Q3? Forces. Here we go. Force on a charge Q moving with velocity. No, action of force from 2-point charges, right? It's just Q1, Q2, so it's just... I'm just gonna write it as K, bro. K, and then you have Q1, Q2, so you have negative Q1, Q3 over, is it A squared? A squared. And it's just a force, there's no, right, there's no vector. This is easy. Plus Q1, Q3, A squared. It's the same distance. Well, you know that this is negative Q1, and you know that this is negative Q1. So this is just positive Q squared, positive Q1 squared. And this looks like you're subtracting it, but it's not. That's what you're doing. This should be 0. That doesn't seem right. Do you add these? You should. Are there fucking answers to this? If there's not answers to this, I'm gonna be very, very upset. Wow, that's insane. Okay, there's no answers. Q1 squared over A squared plus negative Q1 squared over A squared. I mean, obviously you'd add the forces together. But can't you break these into vector components? When was this ever just a magnitude and not a direction? That's weird. It doesn't matter what direction it is, or what component is in what direction, because this just cancels. What is the work required to take charge Q3 and move it downwards until it reaches point? This can't be fucking right. The cumulative force should be... From Q2 to Q3. Q1 squared. Oh, because 1 is in the negative. From Q1 to Q3 is a negative. Okay. So it's Q1 squared over 2a squared I hat plus Q squared. So this is negative Q1 squared times the negative 1/2, which is positive. So again, you have this seems more correct. That's more correct. What time is it? Oh, this isn't squared. What? That can't be right. Maybe it's just such a small number. Oh my god, I'm an idiot. I did 0 to the power of 9. Okay, that's more like it. What is the work required to take charge Q3 and move it downwards until it reaches point P1? This is confusing because this is fucking insane, bro. Downward until it reaches point P1. Dude, I have no idea. It's exactly in the middle of the 3 charges. should be scalable. If you scale down A by 1/2, everything else should scale proportionally. So it should be 3/4 or square root 3a over 4, right? Should be the y distance. That's my guess. That sides are linearly proportional. What is the work required to take charge Q3 and move it? Is that what we're doing? We're taking it. We're doing a potential. That would be solving for a force. We already know that they equal each other. The dipole and a homogeneous electric field. Is it not just the opposite? QD. Vector D from the negative to the positive. I think you might just need to add them. You know that the dipole moment negative times E. How does that have anything to do with the new distance though? Or would it be change in work? Would be the change in electric potential energy. Jesus Christ, man. This is hard. I love how they give us, like, no space to solve it. Like, it should be easy. Is exactly in the middle. What is the work required to take charge Q3 and move it downwards until it reaches point Q? It's Q, so, like... Wait, what is... This is insane. What is Q? Two opposite charges of magnitude. Q. What if they have different magnitudes? I guess dipole means that they have the same magnitude? Okay, so I guess they have the same magnitude. You say Q1 is the magnitude. They always have magnitude Q1. The distance D right now is A. The direction doesn't matter. Same magnitude. These should be the same distance as well. But instead of A, this is what I don't get, bro. They're not one, it's not 1/2 A. Exactly at the center. I don't know what that means. What do you mean center? Center would mean 1/2 A in each regard. So it's 1/2 A. Not 1/A, dummy. Okay. That's not hard. The change in E is different as well. Starting from the initial configuration in the figure, does one need to supply energy to Q2 infinitely far away from the other two charges? What? Starting from the initial configuration in the figure. Does one need to supply energy to move Q2 infinitely far away from the other two charges? What is the magnitude of the work required to move the charge? Maybe it is 0, dude. If the force is always equal and opposite, it doesn't take any type of force to... No, it's got a mass. I don't know. Q2 is negative. So these repel each other and these attract each other. I'm confused on this. This confuses me. This confuses me. Starting from the initial configuration in the figure, does one need to supply energy to Q1 infinitely far to move Q1 infinitely far away from the other two charges? What is the magnitude of work required to move the charge? What's happening at Q1? Q1 is positive, right? Q1 is positive. So these charges are trying to move toward, like, it's trying to attract this way. So in order to move them infinitely away, it's double. You need some sort of force going that way. Yes, you do. What is the magnitude of work required to move the charge? Now this one makes a little more sense because you have two dipoles versus a dipole and a not a dipole. So it's literally P equals QD. Oh, D is a vector. Maybe that's where I fucked up. I'll come back to that. D isn't just like A. D is a vector. That's how P is a vector. So P is a vector equals, it's the magnitude of charge Q1, and then it's A. So in this case it's A distance, but it's in certain directions. So from 1 to 3, it's A times three over 2 is in the y direction, and then it's 1 over 2 in the x direction. They're both positive. Square root 3 over 2. And then it's plus Q1 times A. Damn. But in this case, no, there actually is no y. There's no y direction. 1/2 0. It's 1/2 divided by A, and then 0 divided by A. It's Q1A plus, this is in the I hat, Q1 3/2, Q1A square root 3/2 in the J hat. That's that. And then this is negative, I can just write this out, negative, goddamn, Q1 A I hat minus Q1 A square root 3/2 J hat. And then you're gonna dot that with this. So this is the field on 3, not the field on 1. You need to find the field at 1. So the field at 1 is something. You know, it starts with K. It's Q1 to Q3. Let me just do it real quick. They're both negative Q1. Is it from Q1 to Q3 or is it from Q3 to Q1? It's from Q1 to Q3 because it's positive. It's drawing it in. It's not repelling it. So obviously it's negative 1, it's negative Q1 over 2A squared plus negative Q1 over 2A squared, which just equals negative Q1 over A squared. So it's this is 0. Negative Q1 over A squared, which is 4. So it's that. And obviously it's going to be minus something else. It took me an hour just to do this, bro. What time is it? Jesus, bro. I'm done. I'm done for this exam. This is insane. 8.99 times. Okay, think. It's square root 3. Obviously it's a negative. I didn't do the negative charge, but It's negative 674.25 multiplied by negative Q1. Times A, which is 2. It's just square root 3. Because A is 2. That's what I got. Oh, I was thinking of Q1. Whatever. Same problem with Q2. I have no idea. What is the electrical potential energy of the 3-charge configuration depicted in the picture? Didn't I literally just calculate that? Low-key, I have no idea. What is the electric potential energy? I only have so many equations, and none of these look to solve it. I only have the potential energy of a dipole. That's literally the only potential energy formula I have. If I go back, let's go lecture notes. It's the electric potential times Q. That makes sense. Let me run this through chat real quick. Just see what it gets. I want to see what it does for this. One of my favorites. Oh my god, it's really trying. I feel I'm gonna be sorely disappointed. I can't even play music and listen to and think about this shit. A thin insulating sheet of thickness d is homogeneously charged with a volume charge density ρ, and its center is located at x equals 0. A point charge q is located at x equals b distance away from the charge insulating sheet. We will also consider the location of point p, which is at x equals a. Okay, and that's within the sheet. thick insulating sheet of thickness something. To answer the following questions, write closed form algebraic expressions that give solutions as a function of some of the quantities given above. In order to get full credit, the expressions must be simplified to the most compact form. If the answer is a vector, must give a full description of the vector. What does the electric field do to the charged slab in the center of the slab located at x equals 0? It should be 0. It should be 0. A thick infinite slab. So it's infinitely tall and it's infinitely wide this way in the z direction. But it's not infinitely thick in the x direction. So if you put a cylinder through it, well, you don't have cylindrical symmetry. But if you put a cylinder around it, well, I guess you could just put a box and consider the charges going outward, and then you would see that the charges cancel out. But you're looking for it at the center. At the center. Let's see. This is Gauss for sure. So it's the enclosed. So the enclosed integral, the enclosed surface integral. Wow. I can't write. Of E dA equals, I already forgot, Q enclosed over the permissivity of space, which is just a constant. So E should be constant. If you put a box around it, you should only need to worry about the two sides of the box that are getting hit with charges, or are hit with field. So E should be constant for that slab because the distance from any point to any point on the slab, at the surface of the slab, at any point at the edge, should be 0. I'm definitely missing something here. E should be... This blows, bro. I don't know why this is so hard. It's... Problem is, if you put a box around it, how do you express the area? You can only express the area as an infinite amount. So that can't be it. I know Q enclosed is equal to the charge density, which should be volume per unit volume. Yep. Times the volume that you're looking at. And then obviously volume is obviously going to be We know D, but L and H are infinite, which is what's tripping me up. Plus, how do I demonstrate the electric field at the center is 0? I don't know how to do that, unfortunately. What is the electric field only? Here's the thing, if it was conducting, it would be 0, right? But it's not, it's insulating, so I have no idea. I have 0 fucking clue. What is the electric force on charge Q? Okay, I just need this to get solved for me because I have no fucking idea what I'm doing. Hey, I got this right. Hey, I got that right. F3 is interesting. What is it? What is the electric force on Q3? Apparently it's negative. I don't know why it's negative. What are we doing here? Okay, 0. That's low-key what I fucking thought. To move Q2 to infinity, to move Q3 to infinity. P1 is the centroid. H/3. The external work done to move a charge in a fixed external position is work from 3 to P1 is Q3 times V P1 minus V Q3. Does that make sense? This isn't making sense. Q3 is a charge. The potential times a charge makes sense. Yeah, that makes sense. That's what that is. That's what that is. So there's 0. That's why I'm getting it fucking confused. Yeah, potential energy is the potential times the charge, right? I'm struggling on what P2 is, or P1. What do you mean P1? Yeah, I got this one wrong because by symmetry, P1 is the centroid, 0H3, the external work to move a charge in a fixed external position. Right, the final point is P1, so it's the potential. By symmetry along X equals 0, VQ1 equals X equals 0 equals negative VQ2 at both points, so each total potential is 0. What? What do you mean by symmetry along the X? There is no symmetry along the X. Are you talking about that? There's nothing on this side. I don't... Yeah, it's the charge times the difference in potential. VQ1 equals V. Oh, because the charges are equal and opposite. So each total potential is 0. What? Dude, this is ridiculous. Work to move Q2 to infinity should be 0 as well. Work equals 2Q, or 2KQ squared over A. That's interesting because I got that for... Why doesn't this work? If you look at the forces occurring on Q2, it's... Q2 is negative Q1. It attracts this way, and then Q3 repels it. And same thing here. On Q3 you have a repulsive force pushing it this way. And you have this going this way. Oh, I'm an idiot. No wonder it was negative. It's supposed to go that way. But to move Q3 to P, I mean, it wouldn't take any force in the J. Maybe those cancel. There's like an I hat force on it. This should be negative. This should be 0. This should be 0. I don't know why there's no force in the J hat. Oh, maybe it is. What is this? Maybe it asks for magnitude and I'm an idiot. Squared. No, I don't get the same answer. Electric potential energy of the 3 charge configuration. Oh, this is different. Oh, okay, I got this, but for number 5, why is there no? For number... When you calculate the work to move Q1 to infinity, the relevant quantity is the potential energy of the interaction between Q1 and the other two charges. That's a scalar, not a vector. So in my method, I summed am I doing the same thing? Q1 times A Q1, Q2, KQ1, Q2. What does that remind me of? Force times distance, wow. Because a force is KQ1, Q2 over R squared, and you multiply that by a distance, which gets rid of one of the R's. Damn. Why didn't I think of that? I could have also just done that here. Force times distance. I should have just done FD. Force on a point charge times distance plus force on a point charge times distance. And it gets you a quantity. And then this is the same thing. The potential energy of the whole thing is... yeah, this. Wait, this. And it gets you that. Wow. Okay. I get it. Let's hit this again. I'm gonna hit this again. Or maybe here, let's do... HT2, okay? HT1B, sorry. No, brother. Okay. Let's hit this again. I think I got this. It's the same shit. Just a different question. Ooh. 3 charged balls are arranged as shown in the figure at A equals 2. The ball at Q3 is negative 0.5 times 10 to the negative 7th columns. The other 2 balls have charges Q1 and Q2 equal negative Q1. I'm sorry, charges Q1. I see. So there's 2 different charges. Below, answer first algebraic expression. They calculate numerical values at the result as a vector. Ready column notation. Cool. What is the electric field at the location of charge Q3? Okay, sick. So again, we know that. Maybe we don't know shit. Bro, what is happening? Just write K. It's K, Q, R squared. That's total. It's KQ R squared times delta R of I. So here's what you do. You do K times, so the first Q is Q1. Okay, yep, you've got Q1 over R squared, which is... should just be square root 2. I mean, it's... I'm an idiot. I need to add this to my playlist. Change these pretty lines. Oh my god, this is so easy. You get rid of that. But what is it doing? It's a negative on a positive. So it should be doing positive is repulsive. Q's negative, so it should go that way. I don't know, I just kind of see it as like it's going this way from Q1. It's like something that Q1 exerts on Q3. Because you're looking at the field at Q3. And then Q2. Does that make sense? No, because it's not repelling. It's not repelling it. It's attracting it. So it should be going that way. Right. It's a force guiding Q3 that way. And then this is Q2 to Q3 is negative on negative, which should repel it that way. So it should be positive I. So these should be negatives. Right. No, you follow the coordinate system. Again, is it Q1 to Q3? Because that would be positive X, negative Y. I think it's from... Yeah. It's from the charging question to the point of application. This is negative Q1. But it's in the negative X direction. No, this is fine, this is fine. I'm like tripping myself up for no reason. I'm tripping myself up with direction. There should be two negatives though. I don't know why. Maybe it is from Q3 to Q2. That would make that negative and this positive. And that would make this positive and this positive. Should be negative. Should we just be like 2a squared? No, it's just 2 over square root 2. You're not multiplying them, you're adding them. Negative 2 times 10 to the power of negative 7. Divide that by, oh shit, it should be 4. This should be, because it's negative 2, square root 2a. Okay. What is the electric force acting on charge Q3? What is the electric force acting on charge Q3? Again, we know that force is equal KQ1 Q2 over R squared. And it's a magnitude. But here's the thing. I'm pretty sure you still do this to make it, to give it some sort of directionality. Force acting on Q3. Q1, Q2. Well, it's, in this regard, it's Q1, Q3 over R squared is just 2A squared, which is beautiful. And then again, it's the force on Q3. I think it's from, it's like, what's the electric field at that location? Does it say? No, it doesn't. It doesn't say, like, what. Okay. You do wherever it's pointing minus. So if it's pointing this way, the change was negative, so it should be negative x. Right. That makes sense. Okay. I'm just an idiot. So this should be -1 and this should be 1. Right. And then you add that with Q2 and Q3 over, this should just be -Q1. 2A squared. And then again, it's a negative change in x. Yeah, this is weird. Because I'm accounting for directionality here with the negative charge. From -1, so from Q3, so we should do Q3 to Q2. Q3 to Q2 would be -1. No, Q3 to Q2 is 1, 1. Jeez, man. And then the J should cancel out. One plus -1, yep. Okay. if it was the opposite and I did Q1 to Q3 and Q2 to Q3, it would be a negative number. So if you did this instead, Q2 to Q3 would be negative, negative. That would get you, the J's will cancel no matter what, but a positive plus a positive should get you a positive, and this should get you negative I hat. So you go from the origin of the force, which is weird because it doesn't seem like you do that for the electric field. I don't know. What is the work required to take charge Q3 and move it up by a distance A to a point exactly in the middle between the charges? And the force in the J hat is nothing. What is the work required to take charge Q3 and move it a very large distance from the other two charges? Again. And F in the J hat is equal to 0. There's no work required to move it up and down because the J hats cancel. There is work needed to move it back to the right because there's a force trying to move it to the right. What is the potential energy of the 3 charge configuration? So again, U equals low key, is it just force times distance, which equals just marking them. Is it negative? I feel like it should be negative, no? I like this song. That's already scalar, then the work needed is so you have to do the relationships between all 3. So it's Q3, well oh my fucking god, bro. Q1, Q3 over the distance. This is just a scalar. It should just be a scalar. Q3 and Q1 are different. So it's 2A, or square root 2A. plus. Now Q2 on Q3 is just negative Q1. Again, screw 2A. And then you have negative Q1 on Q1, which is just Q2 on Q1, and that should just be A, or 2A. 2A. It's that. I mean, I don't think you can get it simpler than this. These cancel. Duh. At least they should. Yeah, they should. It's just one minus the other. Oh my fucking god, bro. Negative K times. It's K, not 2, but Q1 squared over 2A equals work equals Q1 squared you divide that by 2A, which is just 4. This is Newton meter squared per column squared. You're multiplying it by column squared, gets rid of that. It's Newton meter. It's a Newton. What? No, Newton meter squared. Newton meter squared divided by meter. It's just Newton meter. Okay, makes sense. What is the work required to take both charges Q1 and Q2 and move them infinitely far away from each other? This is the one question they use to like separate the something from the chaff. I don't know what that fucking means, but you gotta think about Q3 is trying to attract this one. Q2 is trying to repel it. And then these should be repelling each other. If these were like this, no, Q1 and Q2 should attract each other. What is happening? I'm tripping balls. These two should attract. So here's what I'm gonna do. And then Q1 and Q3 are of the opposite charge. Right. Both Q2 and Q3 are negative. So they're trying to repel each other. So these are going this way. And then these are the same charge, so they're going, goddamn. Wait, what? Q1 and Q3 are of the opposite charge. What am I doing, bro? They're trying to do this. They're trying to do this. Goddamn. So yeah, it should. If there should be some amount of work required. And the J should cancel. Because Q1 and Q2 want to come together. J should cancel, and then you're left with a force this way as well. So it's like you add them all up, and you're left with... I don't know how to apply this. What is the work required to take both charges, Q1, and move them infinitely far from each other? Back energy from I have no fucking idea. Couldn't tell you, bro. Alright, let's plug this in and see if we get HT 1.1. What time is it? Oh shit. Thank God, I thought I missed her break. I got fucking really scared. Bro, I sent you the picture. There's only 4 problems. So it seems like you've got point charges considering electric fields, forces, work, and potential energy. You've got the electric fields of charged objects, and you use Gauss law. And then you have this is just electric fields, or I'm sorry, magnetic field stuff and more magnetic field stuff. So heavy on magnetic field stuff. I wish I had started this like Friday, dude, but I low-key had no time. Should have gotten these right. Somehow I got these wrong. shit. Maybe they're right. I fucked that up. Because 1, 1 is not a unit vector. Yeah, they're right. I fucked that up. So I fucked up my unit vectors. That's okay. I can't forget about those. Well, I got this one right. Work to take Q1 and Q2 infinitely far from each other and from Q3. Supplier get back, disassembling to infinity charge from you. So work is required. Yes, you must supply energy. Oh, did I? Hold on. Oh, I'm an idiot. I did it did it opposite. I should be solving for you. U equals K, right, and you get a negative, and then you get, yeah, right. And you just take the opposite of that, okay. Duh. Okay, I want to see how the fuck they solve this, because this is kind of ridiculous. I can do the sphere, I have no idea how to approach. In fact, let me do the sphere right now. What is the magnitude of the electric field at distance R equals R1 divided by 2 from the center inside? What is the magnitude of the electric field at a distance? What is the magnitude of the electric field? So if you did... So you're solving for E. This should just be E times... This would be the surface area of the Gaussian surface. So let's do a Gaussian surface around the first sphere, which is R1. So it would be 2 pi... Oh my god, surface area of a sphere. Pi r to the 4... Pi r squared over 4? Four pi r squared. 4 pi r squared. Q enclosed, which is the entire Q of the sphere, which is just charge density rho times the volume of the sphere. Wow, that's insane. I don't know the volume of the sphere. 4/3 power cubed. Like a little boy. That's it. That's the electric field. There. You know what? If this is just that. What is the magnitude of electric field in empty space to the inside wall of the spherical shell at distance r with arches from the center? What is the magnitude of electric field in empty space very near the inside walls? Yeah, it's equal and opposite. So at the surface of R1, you have PR1 over 3 epsilon 0, epsilon naught. At least that's what I get. Damn. 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 Let's go there. Bro, can't be that difficult. Wow, there it is. That's the charge. mean, you could put. Again, it's that. It's like. Something I'm noticing though is that these need to be the cute in okay, hold on. It's not the same. Because you're enclosing the charged sphere as well. That's the surface area of the Gaussian surface. And then you've got the charge. Well, you're not enclosing any of the charge. In fact, you're enclosing everything right below. Very, very near the inside wall, but not inside of it. So there is no charge. You're not enclosing it. Q enclosed is what you're counting. So it would be the enclosed charge, which is rho times 4/3 pi r1 cubed, so it's the volume of that sphere, the charged sphere. And then you got these canceling. Oh, this is a 3.5. 3. This is what I have. What is the magnitude of the electric field right outside this outer surface? Now these two should cancel. The electric fields of both should cancel. The surface charge density on the outside surface of the conducting spherical shell is mu. Good. I was gonna say I can't use rho. Q onk times what? You're enclosing everything. So it's and now you're doing the surface area of the conducting shell. I see. Yeah, it should act like a point charge. Right. That doesn't make sense. Oh, no, I got it. That makes sense. What is the magnitude of the electric field at distance r equals 2r3 from the center? Really enclosing this. It's not r squared, is it? Well, that's charge per surface area. No. This is 4, because it's this squared. That makes sense. So it is r squared. What is the electric potential right outside the outer surface of the conducting spherical shell at distance r equals r3 from the center? Potential is electric field times distance. That's light work. What is the electric potential in the middle between the outer and inner surfaces of the spherical shell? R2 plus R3 divided by 2.
There's no flux.
The electric field inside should be 0, I believe. That's what I thought. Alright, I need to study this, but I'm gonna take a break. Take a long fucking break. Time is at 10. We're locked in. I got 1 more hour. Ooh. Let's make sense of this shit. I'll denote X as Gauss's law infinite slab. I mean, if I can get that, you know what? Maybe I was overthinking this. I bet the length and width units cancel. Here's the thing. It's a slab, right? So it's infinite in 2 directions, and it's thick in a finite direction. That's given by D. So what you gotta do is go, okay, I give up. I quit school. Oh, that worked. Do this, right? E stays the same, but then you're multiplying E by, it's 2 times length times width. Length and width are infinite, but these should cancel. That equals, I didn't make the equivalency. Q enclosed should be rho, which is the charge density, times length times width times height. Sorry. Length times width times D over permissivity of space. Hello. And then these cancel, bro. Okay, I'm just an idiot. I like that I can solve that. That makes me happy. Is that what they got? Yep. If it's less than D over 2. This is if it's over at the center of the slab. Whoa, 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 whoa. Why are we doing this, bro? Already scuffed, bro. So this is outside. Inside's a different story. It's like the 2 goes away. Why wouldn't it be 2 times length times width? I see why. Because it's the charge density times 2x. Right, 2x over that's why. This is inside. This is outside. Now obviously if x equals 0, what does the electric field only do to the charge slab at point P? What is the electric force on charge Q? Because I'm goated. because I'm fucking goated. Where is it? Force. X equals B. This is outside. Oh. Wait. What is SGNX? Where are they getting that from? The field magnitude outside is a constant. Oh, I see. It's the sine of x. Okay. That makes sense. If x is greater than or equal to d over 2, right? Here. See, it's just PD 2 epsilon naught. What is the electric potential difference from the location? See, this is where I get my jimmies ruffled, bro. What is the electric potential difference between the location of the charge at x equals b and the surface of the slab? Express first the answer as a function of the electric field from the slab at x equals b. Wait, what? As a function of the electric field. No. Huh? I can't tell. I don't know. This is just a bunch of partial derivatives. Okay. This should be easy. just gonna put the negative here so I know that it's R2 minus R1. Sorry, V2 minus V1. Blech. See, this is already difficult. Oh, I already know E. I know E. And E does change with... No, E doesn't change with shit. E equals PD over 2 epsilon naught. That always changes, or that always remains constant. The derivative of L. L has to be distance between the 2 points, right? This is derivative of X. It's D divided by 2. Minus. Okay, I'm getting tripped over L because L, like, this, oh my god, I'm gonna hurt somebody, bro. The L is dependent on, E is only true for values in between, like, from here to here, from there to infinity, in the X direction, positive X direction. So how do I represent that? Well, that's easy. That's easy. It's integrated between D... Oh my fucking god, bro. That's what it is. Right? You're integrating 1. Because that's a 1. Express first the answer as a function of the electric field. I mean, I guess you could factor it out. PD 2 epsilon to y equals 0. To y equals 0? Oh. How high is it? C. 0? I don't know. Because you're not moving it in or out. There should be no change in potential. Because you'd be integrating from B to B, which is just B minus B, which is 0. And you multiply that by 0, and then your change in potential is 0. Should just grow linearly. Please. And then after that, instead of dividing it by 2, oh, it's just constant. It's just constant. Now you do divide it by 2. B minus D over 2. Is that what I got? Ah, dude, how'd I get it backwards? Isn't it from D2 to B, or is it from B to D2? Oh. Oh. He pulled out a negative. Why? Negative. Okay, I got it right. I got it right. If B is outside, okay, which I got. Work is 0, because potential is 0. Alright, I got. Okay. This shit's light. This and this I feel really good about. So I'm gonna go back up to my room, take a break, and then we'll start doing. Who knows? We might. We'll save the last 2 practice exams for tomorrow, so I can just really solidify my my point charge solving by electric field, electric potential energy, and work solving with Gauss's law. This is Ampere's law and magnetic fields and shit. Not fun, but I don't think it's particularly difficult anyway. Well, I guess you can test it out. See if the stream ends if I close my laptop.